No, 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 solo grafici.
Perfetto, ci siamo quindi. Ok, we're almost there. Bear with us. Valerio, welcome on stage. Please welcome him.
Good evening, everyone. I'm also not able to predict strikes, so just if anyone wants to leave earlier. So today I'm going to talk about modeling extreme hail risk, or how to make a simple problem very, very complicated. First, a little bit about myself. I'm a senior data scientist at Lightsource BP. I do a bit of optimization, forecasting, statistical modeling. Before that, I was at Tesco, where I was doing forecasting, and I work in the recommendation team as well. And before that, I did my industrial PhD at Square Enix in partnership with the University of York. In a previous life, I also got an MSc in clinical psychology, but didn't help coping during the PhD, not at all. A little bit about Lightsource BP. Lightsource BP, my company, is a leading developer, construction manager, and operator of global utility scale for onshore renewable energy. And our purpose is to deliver affordable and sustainable power for businesses and communities. How do we do business? We develop, build, manage, and operate and own assets, along with some partnership with other entities. Since no man is an island, these are my amazing colleagues that unfortunately couldn't be here. Anna Lyons, Joseph, and Pritin Patel, who is my boss. I have a couple of disclaimers. But before that, going to give you like a brief agenda on what I'm going to talk about. First of all, I'm going to say, I'm going to present a simple problem with a simple solution. Then I'm going to give you like a brief statistical overview on hail event, extreme hail event in particular. And then I'm going to turn the simple problem into a complicated one and maybe try to find like some complex solution for that, like present some canonical approaches on estimating extreme hail event, and then presenting some Bayesian regression approaches on estimating hail event. Raise of hand, who is familiar with Bayesian statistics a little bit? Awesome, okay. So no, I cannot, I can skip the details. First disclaimer, what I'm going to present here is not connected with Lightsource BP or its operation, nor use company data. I'm using like open source data for this. This is just part of my team R&D effort. How does it look like? Usually I go to my boss and I say, please, 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 can I do a pet R&D project? And he says, yeah, make it quick, but have fun. Disclaimer number two, I'm gonna go in to make several simplifications here. And also some choices will look arbitrary, just bear with me. So I have 70 slides. I'm not sure I'm going to be able to run through all of them. Then you can ask for the details later. So the simple problem with a simple solution. Also, I don't know if maybe this is the right position. Problem statement in short, quoting the favorite game of Joe, my colleague, oxygen not included. Solar panels cannot withstand meteor strikes. This means that they must be protected from direct damage from cold materials falling from them. That's very basic. Stuff falls from the sky. You have a sea of glass. You have to mitigate the risk or take mitigating action for avoiding damages. Problem statement in a bit more details. This is a hailstorm in Texas. These are golf ball size hailstone. And you can imagine the damage that could do. The cow is running for its life. So we have to estimate the likelihood of these events happening, also maybe with some level of uncertainty around our estimation, so that we are able to assess risk for people and for infrastructure. Thankfully, in the US, but you also have resources in Europe, the NOAA weather program have amazing resource for this. They have a hail record data set that goes from actually the 50s up to 2024. 2025, it's updated regularly, but this analysis run up to 2024. So the simple solution to this, we can just compute the empirical probability for every part of the US. And voila, presentation finished. Thank you for your attention. Unfortunately, it's not that easy. And here's how we try to make the simple problem a little bit more complicated. First of all, these are type of hail sizes categorized by severity. We go from a pea up to a grapefruit. And the amazing thing is that with increased severity is decreased severity, meaning the things that are most damaging are also most rare. And as you can see here, the red dots are 2.5 inches or more, meaning hail storm that can create serious damages. And you can see on the right that these are not very common, and they are also very scattered around. These are not very frequent, and when you go from simple hail to extreme hail, you also have areas in which you don't observe any, or you observe very few. Indeed, hail distributed and over-dispersed distribution. So we have a long tail, and we have a lot of mass in the area around 2 or 4 hail events per hour. We're talking hourly granularity here. And when we take the data and we pad it so that we have a continuous time series, we have a 0.5 million extra rows, all zeros. That means that our data is made mostly by 0 because, of course, it doesn't hail every day. Like, it happens once in a while. On top of that, the distribution of hail sizes is your average risk manager worst nightmare. So the bulk of the distribution is where the hail size is below 2 inches. We basically don't care about it. And is also the most useful for estimating any parameter. What we care about is the tail that doesn't have a lot of occurrences. And if we try to fit a conventional distribution like Gaussian to that, it's a mess, because the tail basically is not able to capture any of the events, just cut off where we most need it. And on top of that, we have seasonality, and the seasonality changes different quantiles of hail sizes. So what you hear here is the seasonality at hourly, monthly, and yearly level at different quantiles of hail size. And as you can see, the more you go up, the more the seasonality is pronounced. And we also have spatial effect. And they also change based on the quantile of the magnitude. As you can see, at the 25th quantile, we basically have no pattern. And when we go to the 95th or 99th percentile, we start to see a pattern emerging. On top of that, as I said before, small area population become a problem. States like Texas is like the prime example of a hail state in the US. Analysis there will be easier because we have a lot of data. But in a place like Florida, where we have hail once in a while, but we also have the ice bomb that I described before, well, the analysis will be harder, but it's also the place where it's most important to run the risk analysis. And the problem of small population happens also in states with very frequent event. In this area of Texas, you basically see that there is not a lot of hail happening on the left. But on the right, you see that there is a lot of potentially dangerous hail event happening. So we have to create a few extra problems that now we need to solve. We need to account for a zero-inflated, over-dispersed distribution, and we have to focus on the tail of it. We need a good degree of spatio-temporal resolution, at least at the county level for US. It doesn't make sense to say risk of Texas is X. Texas is huge, it's big as Italy. We must consider some seasonal and spatial effects, and we also have to find a way to correct for a small area population. And if we should throw also some uncertainty estimation in the mix. My job description says that I have to solve this using a model, but we'll see how it goes. First of all, like a very canonical but principal way for evaluating this type of problem is to use extreme value analysis, which is estimating the probability of events that are more extreme than any previous observed. How does it work? It's very simple. You find the yearly maxima, you rank them, and then you calculate the yearly return period. So how you define the maxima? You have like the sequence of your events, and then for each year you take the one with the highest value. If you take that, then you get the distribution of maxima, and you can easily compute empirically the return period off of this. I'm going to explain later what we mean by return period. Not a lot of science, a lot of data. All happy. We can finish this in half an hour. Mind the interpretation of the result. When we say that a 3.5-inch hail event has a 10-year report period, does not mean that it has a probability to return in 10 years. It means that every year we have 1 in 10 chances for the event to manifest. We basically assume that the maxima are independent events and they have a probability assigned to it. Then we can translate it into years. Unfortunately, doing it empirically means that we never observe a 100-year event. We have 25 years of data. We cannot get an event in 100 years. And also, if we have one big outlier, it messes up the whole thing. Is that event a 1 in 1,000 year, 1 in 10 years? Who knows? As we said, is an independent event. Another way that we can do this is to fit a distribution. So we find the maxima, we fit what is called the generalized extreme distribution, then we extrapolate using the distribution CDF. As you can see, on the left, we have the gen extreme distribution. You see how it perfectly captured it. Not perfectly, but like it does a better job than the Gaussian distribution. And once we have that and we have the CDF, we can basically invert the CDF, and then we can extrapolate up to 100 years. As you can see here, we have a fit to our empirical values that we've calculated, but we also can now say, okay, 1 in 100-year event is a 6-inch hails. And we can do that for each county in a state and fit distribution to each data in each county, and then we have our nice estimation for each of the county. This is an extremely principled approach for doing extreme value analysis. It's actually the most statistically sound. Gen extreme distribution is proven to be the best one at describing maximum. Unfortunately, it has some drawbacks. It relies on many strong assumptions. Converges slowly, so like you need a lot of data to get a good fit, and of course, if it's rare event, you don't get a lot of data. It can provide physically implausible values. Like you see there, like 1 in 100-year event is 7 inch. That is 7 meters. Like it's massive. That's a statistical error, let's say. The confidence intervals are wild, are huge. This is not a bug; it's actually a feature of the distribution. And there is awkward parameterization of the distribution. It's very hard to work with. An alternative that we can take is to use Bayesian regression. That can help us ironing out a few of the problems that I outlined. How am I doing with time? Good, cool. First of all, we break up the problem into 2 sub-problems. First of all, estimating the magnitude of rare events, so how big, when a rare event hits, how big it is. And then estimating the likelihood of an event happening, like how likely the hail is gonna hit. For the first one, we're gonna use quantile regression for estimating the magnitude. Quantile regression basically is, instead of estimating the expectation, we estimate the value that describe one of the percentile in a distribution. And for doing that, we use the quantile asymmetric Laplace distribution, which is an amazing distribution. Basically, the location parameter of that distribution, the dotted line, tells us the quantile. As you can see, if we pick the 50th quantile, the distribution is symmetric, so the density falls equally on the two halves. For the 95 quantile, all of the mass of the distribution is on the other side, meaning that our location parameter describes that part of the distribution where most of it falls on the other half. And for estimating the likelihood, we can use a inflated negative binomial regression, which is basically has this form. You have a latent variable, is called a gate, that tells you the probability that the event happens. And the gate is going to condition our observed variable that distribute negative with a negative binomial distribution. So what is happening is that we get an excess of 0, because if the gate tells me that I don't know, I have a 99% probability to not see hail, I'm going to have a lot of 0. Only 1% of the cases I'm going to sample from the negative binomial distribution. For estimating this regression, we use what is called a generalized additive model. It helps us account for seasonal and spatial effects. Instead of a simple regression, we basically sum together smooth nonlinear function. So for instance, one function can take care of the temporal aspects, and another function can take care of the spatial effect. For modeling this function, we use splines. I think many people knows about it. It's a very, very flexible way for modeling nonlinear function. And the nice thing is that you can do them in 2D as well. So if in the 1D case, we can use it for temporal elements. In this case, distributed 2D, we can account for spatial components as well. Of course, we can also use a more sharp way for defining the spatial effect by just using the structure that the county provides. Basic statistic core idea, I think I can skip. The general idea is that we think of parameter as random variables, like we have a prior model, you know the jazz. How to implement that? My choice is to use JAX and NumPyro because it's a perfect marriage for doing fast and customizable probabilistic programming. JAX helps us speed up computation and has a NumPy-like interface. This function here is like the RBF kernel for a Gaussian process. In dark line is the execution time for simple NumPy. The lighter line indicates a function that has been JITted, just-in-time compiled using JAX. I think you had talk about this probably in the previous PyData. NumPyro allows you to write models like you would do in NumPy. This is like a simple linear regression. You specify your priors. You have sampling nodes for random variables, plate notation for enumerating your variables automatically, deterministic node where you can put computation. And that's the perfect place for putting JITted function. Imagine you have your probabilistic program model, and then you say, okay, I want to do some computation on the probabilities that the model creates. You create a deterministic node, you slap into there like a Python function that has been JITted, and you can also compute that inside the model. So quantile regression, we use partial pooling for pooling information from all counties. And basically what you see here is the priors for every coefficient inside the linear model. And then basically we exponentiate whatever comes out of it because a quantile cannot be negative. So we enforce positivity by that. Then we plug that into our asymmetric Laplace likelihood, and we fix a certain quantile so that we can estimate a specific quantile. Why doing partial pooling? Because it allows to share information across parameter. If you remember, I said small population is a problem. If we partially pool information across counties to a single common parameter, it means that counties that have very few data points can take information also from the other counties, if it's helpful. On top of that, also helps regularizing the parameters, so we kind of smooth out the outliers. As you can see here, this is the result from the special effect. Remember, this is Bayesian, so every time we estimate something, we get a distribution. You see on top the distribution of the special effect for that specific county. It's kind of nice, that gets you like a level of uncertainty of how the distribution is for that specific county. It's a county, I believe, that has very few fail events, but some major one. So like it's highlighted as one with a potential high level of magnitude, but also the distribution is quite wide. And of course, we also get the yearly, monthly, and hourly component, as we would do with our nice shaded area for uncertainty. This just gives us an idea of how different year, month, and hour contributes to our estimation. What we can do also is to partially pool not just simply an intercept, but a spatial component. What does allow that? That's the comparison between the two. As you see, if we only have a fixed intercept that is not spatially aware, we get a block for each county. While if we partially pool like a spatial component with a nice gradient, because a county is also like a big area. So like we can have hail, different hail magnitude in different areas of the county. This looks a bit like a monster, the zero inflated regression. It's actually quite easy. It's just like a lot of notation. It's basically two models together. The blue part, that is one taking care of the gate, is a simple simple linear regression with exponentiation at the end for enforcing positivity. Sorry, I inverted the colors here. But basically, like the gate is a simple logistic regression. It outputs like a probability between 0 and 1, while the other one is a simple linear regression. And the nice thing is that also we can visualize the various parameters spatially. So the gate in this case tells us where is most likely of a hail event to hit. If it's darker, it means that there is a higher probability. If it's lighter, it means that there is a lower probability. There is a nice interaction here because you can have a place with a lot of hail, but small magnitude, or you can have a place with not a lot of hail, but a huge magnitude, or the chance of very rare. Also here we get our temporal components as before, but like you can see, is more pronounced. You see the peak is around 3 in the afternoon and in the beginning of the year. Florida is a hot state, so like you tend to get hail at the beginning of the year rather than in May. So how can we use these models for assessing risk? Well, we can sample trajectories from our zero inflated model. So what you have on the right are I believe 10 years of simulated hail events sampled for 4 different countries. The spikes are number of hail events at a specific hour. And once we get that, we can map these events onto our magnitude map. We know that of these events, 5% are likely gonna fall within the extreme event. So we just pass those events with characteristics, meaning location, time of the year, yada, 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 into the regression for the magnitude estimation. Basically, almost everything I presented today was based on someone else's work. That's the deal of data scientists. We don't invent anything, we just reuse. So like I encourage you to check these resources and credit goes to them. some much smarter people than myself. And yeah, thank you for your time and attention. Questions?
I will open the other ones. Okay, there was really something. Questions?
Any?
Okay, one from the very bottom of the crowd. Secondo me questo non funziona, però ti sentiranno.
Maybe thank you for the talk. Maybe it's a stupid question, but your approach seems based on a white box approach. Did you try gray box or black box estimation models?
So I asked ChatGPT to produce the return period before this talk. It didn't go very well. No, seriously speaking, I think if you go to much more complicated models, you start to include, I don't know, environmental variables, weather, I don't know, temperature, then elevation, and other type of things. These type of models are a bit hard to work with because, as you said, they're white box, like they give you a lot of visibility, but it's also hard to make them adjust when you have a lot of covariates. One thing that I experimented in the past, you can have one of these models for the core components, and then you get something like a neural network that does feature extraction for the covariates. Let's say you have 200 covariates, you let the neural network take care of that, and then you input that into the model, and you say, okay, I have my time, my spatial, and then this part here is the magic sauce that just round everything up.
Another question. Right.
Thank you for your talk. My question is, so now that you have this estimation, how do you use it? So for what? For what kind of use case? And the other question is about the data sources for Italy or Europe.
Yeah.
Is it good? Is something similar to this?
Okay, so first one is application. I don't think these are models for to be used for, let's say, operationally, meaning I have a site or I have a place where I have something and I want to act on that site. These are more risk management kind of tools. So like, as I said, like my company take a different route than this. But in general, like what you say is that like you would give this to like someone that has to assess a risk, has to take decision, and you can provide it as a decision tool to them. The nice thing is that once you have the model and the estimation, as I said before, you can plug in different things. Like you want to simulate an event for the next 30 years, and then maybe attach a cost to it. And then to the cost, you want to attach inflation, and maybe you want to attach something else. Then you plug into the model, and then you get a nice projection of what happens if something bad happened in a given area. And then it gets you like a bit of an idea of how much exposure you have there. With regard to the, I don't remember the exact source, but I know for sure that Italy and Europe have this type of resources. But I believe that differently from the US are closed source, as in you have to submit a request for research or some kind of thing for getting the data. But I think something from the European Union, but I'm not entirely sure.
Thank you.
Oh, ok. Il destino che io mi domando.
I'm not really sure this question makes sense, but have you tried any kind of non-parametric approach, like bootstrapping, even just as a baseline to compare your parametric or Bayesian predictions?
So I prepared the code for this talk in a couple of weeks. So I just barely had the time to do what's on the slide. But if I would have to do this for real, I would definitely do bootstrapping, especially with the empirical distribution. Right? Like you get the data, you can compute the empirical. Basically, that gives you the probability that a hail event, then you compute it for every hail sizes, and then you just simulate out of that. That's actually a very, very, very good baseline, because if that works okay, why do you have to build a model?
Thanks.
Scusa? Ah, okay.
I was thinking about climate change, and I mean, as everybody knows, and is in the word, in the mouth of everyone, I guess the frequency and the severity of this phenomenon has really changed in the latest years. Like, how did you, how well did you see your model perform in terms of like using older data to predict these like newer years and the severity of these newer years?
That is an amazing question. There is a Nature paper about the hailstone dichotomy. Basically, like we see that in some places in the US, the likelihood of hailstorm is going down, but the likelihood of extreme hailstorm is going up. So that's a bit of a picture for the reason that I said before. How do I see that? Like, the fact that these things are happening is a given, and they create this sort of problematic situation. The things that they're slowly moving to a certain extent. So I don't know if I can super rapidly. Let's see. Pop, 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 pop. No. So the year component is basically your trend. For Florida, is flat. So nothing is really happening. If you look for Texas, it's going upward. The point of a trend is that it gets you a general direction where things are going, but trends are slowly moving. So like you have to take into account climate change for this type of estimation. But if you go off, I don't know, 10 years, you're pretty certain that things will change, but not dramatically. The problem is when you go a much lower granularity and you want to predict what happens the next hour. That's where you really have a problem, and maybe you use one of those black box models for being a bit more flexible.
I would like to ask a question. If you switch to the gradient size slide, I was surprised to see, oh my God, getting closer, it's really hot. Why here you have like a really solid tall gradient and on the boundary it just drops down immediately?
Because, can I move?
Yes.
Sorry. So I also fit in another model, but I spare you. This is a model where we don't have the counting, but we only have the gradients. The gradient is amazing because it gets you like the effect of latitude and longitude on what you're estimating. But actually with the county, you can have sharp changes because like, I don't know, you have mountain and something like that. Or the terrain change. So you fit this gradient, but you let it vary by every county. Every county gets its own version of this gradient. So it can go up for one county, it can go down for another, like it can change depending on the geography. Of course, the assumption is that the model is correct, but in principle, it allows you to. So like in some areas, it's continuous between counties because it's natural, but in some areas, you have like a sharp change. If I go, so, and this is going to be, oh, so much clicking.
I remember the one.
you see also from the counties here. So I'm gonna move in this area. Some counties have continuous plots that move from a county to another. Other areas, like here, there is no continuity. So like there is no sense for the spline there to continue in that direction. Of course, it can also be an artifact of the model.
Okay. Thank you very much. No more questions, I suppose? I will give a really huge round of
Thank you.
applause. Thanks again for BCG for hosting us and having us tonight.